Hi, welcome back. In this section, we're going to learn some of the physiology related to the respiratory system, specifically what is known as the oxygen hemoglobin dissociation curve, which from now on, we're just going to call the oxygen dissociation curve. What this curve shows us on the X and the Y axis, on the y-axis is the relative amount of hemoglobin that is going to be saturated with oxygen. And we look at it at the function of the surrounding oxygen levels. So here's what a curve would look like. On the x-axis, this is the partial pressure of oxygen, all the way from 0 to 105 millimeters oxygen, which is what you would find in the lungs. And then on the Y curve, we are looking between 0 and 100%. And part of the reason why I like this particular curve is because it has these little drawings, which are essentially showing a hemoglobin molecule. And if you recall, a hemoglobin molecule has 4 globins, each of which has a heme, in the center of which is an iron that can attach to an oxygen. And so this is showing like this 4 cloverleaf thing. And at the bottom at 0%, none of those globins have an attached oxygen. And then at 25%, envision that all of them would have 1. At 50%, envision all of them would have 2. 75%, all of them would have 3. And 100%, all of them would be fully saturated. Okay, now in reality, there's many ways of getting to 50%. Each one doesn't have to only have 2. You could have some that have 4 and some that have 3 and some that have 2 and some that have 1. But for right now, it's just a more simplistic way of looking at it. So what happens when oxygen binds to hemoglobin is that hemoglobin changes shape. So way down at 0%, the hemoglobin, the 4 chains, when you look at the quaternary structure of hemoglobin, it's quite compact. Okay, so it's very hard for that first oxygen to bind. Once that first oxygen binds, that actually changes the shape of hemoglobin. So it's not as tight, it's expanded a little bit, which means it's easier for the second, the third, and the fourth one to bind. So when we are looking at this, what we can see is as the red blood cells are passing through the alveolar capillaries, which are very high in oxygen, over here on the right side, that's where hemoglobin is becoming saturated with oxygen. So by the time it's leaving the pulmonary capillary bed, we should have nearly 100% saturation. Normal values would be, 98, 99% saturated. So when we look at the curve, what you notice at the far right, there is a plateau over there. And that plateau has to do with where we are adding that last oxygen, going from 75 to 80 to 85. Basically, we have to have very significant increases in the partial pressure of oxygen in order to have one more oxygen attached to it. In contrast, the steep part of the curve is showing how easy it is for oxygen to be offloaded from the hemoglobin. So as the partial pressure of oxygen is falling, as you're going from highly saturated arterial blood in the lungs to looking, for instance, where blood is in the tissues, more and more oxygen is going to be offloaded in the steep part of the curve. So here what it means is small changes in the partial pressure of oxygen can give us big changes in the relative saturation. And that's how we want it for if we're dropping off oxygen to tissue. So now that I've kind of gone over this all with you, I'd ask you to pause the slide here and kind of go through all of this by yourself to make sure you truly understand this before I talk about some specific numbers. Okay, did you do that? So let's continue on then. So let's look at a curve that actually has numbers on both. I'm going to talk about different things, but first let's talk about oxygen saturation. As I said, if we look at the far right part where we've got a PO2 of 100 in our alveoli, what we can see is nearly all four of the irons on all the heme molecules attached to the globins are bound to oxygen. We have near 100% saturation going on. The next thing I want to point out is, where does the 50% oxygen saturated occur? So if we go down on the y-axis to the 50 point, it's right here, meaning at this point, half of the hemoglobins will be bound to oxygen. And if you look where that is on the x-axis, you will see that is at a partial pressure of oxygen around 27 millimeters of mercury, okay, which would not happen anywhere on the arterial side, but it would be on the venous side. So now that we understand 50% oxygen saturation, let's look and see what normally happens at rest and what happens at exercise. So at rest, when the red blood cells are passing through the systemic capillaries and going from the arterial side to the venous side, what we have is a partial oxygen level of 40%. That's the typical ones, which means if you follow the 40% all the way up to where it intersects the red curve, you will see that just right around 75% saturation still exists. So this is what I've been talking about earlier in this course when I say when we talk about venous blood as being deoxygenated, it's really not deoxygenated, it's usually partially deoxygenated. Because if we think that at rest, the normal PO2 is 40%, that means we're still going to have around 75% oxygenation, which means the blood could go around again and give up some more if it needed to. Now, in contrast to this, at exercise, and I don't mean like regular exercise going for the walk, but think like you're an Olympic athlete and you are competing. So strenuous exercise. When those red blood cells are traveling through the systemic capillaries, there's a very low oxygen content. Why? Because those cells are using up all that oxygen to make the ATP so the muscles can contract. And so at that point, instead of having a PO2 of 40, which is what we have at rest, the PO2 at strenuous exercise could drop all the way down to 20. And so if we take that 20 value for the PO2 and we see where it intersects the red line, what you will see is it intersects the red line with only about 35% of the oxygen still being attached to the hemoglobin. In other words, when you're exercising, your red blood cells are giving up more than the one oxygen per hemoglobin that they're giving up when you are at rest. So in this case, strenuous exercise, they're giving up either 2 or 3 oxygens. All right. So at this point, stop it once again, review all of this and make sure you understand it. You now have all this information on one slide, which is the slide that I gave you in your packet. So now let's talk about shifting this curve, okay? Because shifting this curve tells us whether or not we have an increased or a decreased affinity. So when we're talking about shifts, we either talk about a right shift or a left shift to it. So in a right shift, what that means is there is a decreased affinity for oxygen. In other words, the hemoglobin is not going to hold on to the oxygen nearly as tightly. So in a right shift, it's giving off more oxygen than expected. So what gives us a right shift? Well, when you have an acidosis or high CO2 levels, or when you have a fever, and if you have sickle cell disease, all of these cause a right shift. And so We also have what's known as a left shift, which is essentially the opposite of a right shift, meaning that we're going to have an increased affinity. So we're holding on to it much tighter. We're less likely to unload the oxygen. And so most of these things are the opposite as what you would have causing a right shift. The one thing I want to point out on here is carboxyhemoglobin, and carboxyhemoglobin is what happens when you're breathing in carbon monoxide gas, and it's shifting everything to the left. And what that means is it's holding on to the oxygen much tighter, meaning it's harder to release oxygen to your tissues. So this is how carbon monoxide poisoning kills you. The carbon monoxide is binding to the exact same place the oxygen would bind to, and it's not letting go. Plus, it's preventing whatever oxygens might be bound to the hemoglobin from being released. So it's like a double slap in the face going on. All right, so what do these curves look like if they're shifted? Here's an example showing the normal curve in blue, a right shift in the brownish red color, where we are unloading more oxygen at higher PO2 levels. And then the left shift in green, where we are holding on to it tighter. And so you can tell we're holding on to it tighter because at lower levels of PO2, we have higher degrees of saturation than normal. So go ahead and pause it here. Make sure you understand this right and left shift. And of course, any questions you have on oxygen hemoglobin dissociation curve, please be sure to write them down and bring them when we meet again in class. And with that, I'll see you shortly when we continue this exploration of respiratory physiology. And thank you once again for all your hard work.